All right, let's just jump right in. We talk a ton about artificial general intelligence, AGI. But what if the secret to building a real thinking machine isn't just about making our current AI bigger and bigger? What if it's about giving it a completely different kind of brain? Or maybe, more accurately, giving it two of them? So get this. Right now, a single top-of-the-line AI data center can burn through over a megawatt of power. I mean, that's enough juice to run hundreds, maybe even 1,000 homes. All of that just to run one giant AI model. It's a truly mind-boggling amount of energy.
Now, look at this number, 20 watts. That's it. That's all the power it takes to run the supercomputer that's processing my voice right now, the one inside your own head. Yep, the human brain. It is millions of times more energy efficient. So what gives? You see, this insane energy gap, it's not just a simple efficiency problem. It's pointing to a much deeper issue, what you could call an architecture crisis. The very foundation of how we've been building computers for the last 80 years might actually be the thing holding us back from real AGI.
So here's how we're going to break this all down. First, we'll look at this hidden crisis. Then, we're going to borrow a really cool idea from psychology. After that, we'll explore the wild new hardware that's being built to solve this. And finally, we'll ask the big question. What does this all mean for the dawn of AGI?
So here's the fundamental issue. Our current strategy for AI, basically just making the models bigger and throwing more data at them, is hitting a massive wall. We're getting smaller and smaller improvements for a cost in energy and data that's just shooting through the roof. It's totally unsustainable. And the reason for it, well, it goes all the way down to the nuts and bolts of our computers.
It's something called the Von-Neumann bottleneck. Okay, imagine your computer's brain, the processor, is a busy workshop, and its memory is a giant warehouse, but it's down the street. For every single little thing the workshop needs to do, a truck has to drive to the warehouse, pick up the data, and drive it all the way back along this tiny one-lane road. This constant back and forth, this data traffic jam, is what wastes almost all the time and energy in modern AI.
Okay, so if the old architecture is the problem, how do we fix it? Well, the inspiration for the solution might actually come from a Nobel Prize-winning psychologist, Daniel Kahneman. He came up with this brilliant idea that our own minds have two completely different ways of operating, and it turns out this model maps perfectly onto computer hardware. He called them System 1 and System 2. System 1 is your fast brain. It's your gut reaction. It's intuitive, it's automatic. It's the part that instantly recognizes a friend in a crowd or makes you slam on the car brakes without even thinking. Then there's System 2. That's your slow brain. It's deliberate, it's logical, it's methodical. It's the part you have to consciously turn on to solve a tough math problem or plan out a detailed strategy. And right here, this is where it all clicks. Our current AI, the stuff running on CPUs and GPUs, it's a System 2 beast. It's fantastic at those slow, logical, step-by-step tasks. But it's horribly inefficient when it tries to fake the fast, intuitive thinking of System 1. For that, we need a whole new class of hardware. Neuromorphic chips. These things are designed from the ground up to act like a real brain. So what makes these chips so special? Well, it really boils down to three revolutionary ideas. First, they do the computing right where the data is stored. The workshop and the warehouse are in the same building now, so there's no more traffic jam. Second, they're event-based. That means they only use power when something actually happens, when new information comes in. The rest of the time, they're just sitting there using almost no energy. And third, they communicate using spikes, tiny, efficient pulses of electricity, just like our own neurons do.
And the results? Well, they're pretty staggering. For tasks that are a perfect fit for that fast System 1 style of thinking, a neuromorphic chip like Intel's Loihi 2 has been shown to be up to 100 times more energy efficient than a standard CPU. This isn't just a little bump in performance, it's a whole new ball game.
So this is the really crucial idea. The future isn't about replacing our old logical computers with these new intuitive ones. No. The future is about building a hybrid brain, fusing the raw power of System 2 with the incredible efficiency and speed of System 1. It's about getting the best of both worlds. And I know this sounds like science fiction, but it's already happening. Researchers at Tsinghua University have actually built a working prototype. It's called the Tianjic chip, and it is the world's first ever processor that can run both brain-like spiking networks and traditional AI networks on the very same piece of silicon. To prove that this thing actually worked, they did something incredible. They built a self-driving bicycle that was controlled by just a single Tianjic chip.
And it's the perfect example of these two systems working together. You have the bike's camera using a traditional network to see an obstacle and plot a course around it. That's the slow, logical system 2. But at the exact same time, the neuromorphic part of the chip was handling the constant, tiny, moment-to-moment adjustments needed to keep the bike balanced. That's the super-fast, super-efficient System 1 reflex. 2 brains, 1 bike.
Okay, but wait a second. How on earth do you get two totally different kinds of computer brains to talk to each other? Well, that's where this tricky concept called Vector Symbolic Architectures, or VSA, comes in. Think of it like a Rosetta Stone for AI. It's a mathematical trick that lets you translate the fuzzy, pattern-based language of the System 1 brain into symbols that the precise logical System 2 brain can understand, and then back again. It's the bridge that lets intuition and logic have a conversation.
Now, I don't want to make it sound like this is all a done deal. It's not. There are some massive engineering hurdles to overcome. Just converting the signals from one system to the other costs energy, creating this interface tax. And right now, we don't have a standard programming language, let alone an operating system, for a two-brained computer. Plus, sometimes, when you translate between these two worlds, you can lose a little bit of information, kind of like a bad translation.
So where does all this tech go from here? And is everyone in the AI world even convinced that this is the right path to take to get to AGI?
Well, most researchers see a pretty clear roadmap ahead. Right now, we're in the phase of using these neuromorphic chips as separate coprocessors. In the next 3 to 5 years, you'll probably see them integrated onto the same package as a CPU, what they call a chiplet approach. And then, maybe 5 to 10 years out, we could see truly unified, mature hybrid chips like Tianjic become the gold standard for any serious AI.
But you have to know, there's a really powerful counterargument to all this. AI pioneers like Yann LeCun basically think this obsession with fancy new hardware is a distraction. He argues that the real breakthroughs are going to come from better software, from smarter algorithms that can run on the incredibly powerful GPUs we already have. From his point of view, the hardware itself is secondary.
And this brings us to what might be the most crucial takeaway from all of this. The debate over software versus hardware is gonna rage on, for sure. But for any AI that actually has to exist and act in the real, physical world, think about a robot, a drone, or a self-driving car, that insane energy efficiency and the real-time reflexes of a System 1 brain, well, they aren't just a nice feature to have, they're an absolute necessity.
Which leaves us with one final, pretty profound question. As we start building machines with these two brains, one that has intuitions and reflexes, and another that has logic and reason, are we just building a more efficient machine? Or are we actually taking the first real, concrete steps toward building something that can genuinely think?